So, the next thing I started talking a little bit about fitted queue iteration. So, the idea behind fitted queue iteration is very simple, right. So, essentially what you do is you gather data of the form right. So, this is exactly what you do in LSTD, right, and what you do in fitted queue iteration? You do what?
You generate data from the initial queue that you have and then learn the.
So, essentially you learn the thing. So, I have my SI comma target I, this will not really be SI, it will be right. Is it correct? Is there something wrong? Right. And then what is target I? Right. So, this is the target. So, I form a set of tuples like this, feed it to the function approximator, right, and then it will train something, it will spit out a new q hat, right, and then I go back, I do the same thing again, right. So, what is the requirement that I should have? That I should be able to run this max, right. So, that essentially means that I should have taken that all state action pairs, right. I mean, otherwise I really have no meaningful data on which I am estimating that max, right, or I have to take at least similar looking state action pair, so that I can use my function approximator in order to generate the values for those, right. So, the static training data that I work with, right, the static training data I work with should be broad enough, right, should be representative enough, so that I sample all kinds of state action combinations, at least modulo my phi, right. So, what do I mean modulo my phi? When I look at the phi of S comma A, I should have sampled enough of those representations, right, and need not necessarily sample every state action pair, right, but I should have sampled it enough, so that across the phis I have sampled all possible state action combinations I will see. Some amount, so that the generalization is useful. Okay. So, this is essentially fitted queue iteration, right. One very popular version of fitted queue iteration is essentially neural fitted queue, or sometimes called NFQ. So, what do you think neural fitted queue does? Exactly. Right, you make these data sets, right, you make this data set, feed it to a neural network, right, and then the neural network chugs away, and then it gives you back a new q hat represented by the neural network, and then you create another data set and you keep giving this to this until it converges. Okay. So, what are the problems that you might face when you are doing this? One I already told you. What? What's the, I mean, I discussed one problem already with you. What is the problem?
Static data should have enough sampling.
Yes, exactly. So, you should make sure that you have enough samples in the data, right. So, that is one problem, right, and another problem is in general for any function approximation. What is the other problem? Huh? Let us assume that I have a way of doing max on this. Yeah, of course, max is a problem, but suppose you have small number of discrete actions, right. I can train one network for each, and so I can just evaluate each one of those neural networks and then figure out which is the max, right. So, So, if you have small number of discrete actions, you can get away with that. You remember in the very beginning I was telling you, for representing Q you have multiple options. So, one of them was to have different networks for different function approximators for each action, and in this case you will have different neural networks for each action. But what is the other problem that you could encounter? This is not something peculiar to what I told today or yesterday. It is a problem with all kinds of function approximation.
What do you mean you feed it to an approximator and it puts out a new Q?
Which is what we have been talking about for the last 2 days.
As in gradient?
Whatever is your favorite training algorithm, you use it, right? I'll give you training data, right? It's a regression problem. Solve it using whatever is your favorite regressor. Right?
So what do you mean when you said you have a different neural network for each action?
Why not? It takes the state as an input, gives QSA as the output.
That is only okay. If you have small number of these.
You should revise from previous classes. This is one of the options I gave for doing control with function approximation. Right. In fact, I indexed the phi with the a as a subscript. Right. I said phi a of s is something that you can use. That's one different feature sets you could use for different actions as well, and so on and so forth. And then I also had a theta a, and so we looked at all of that. So what is the problem? Jenna knows the problem. What is the problem? Oh, come on, you know that.
Non-stationary.
Huh?
Non-stationary.
Yeah, but I'm not solving a non-stationary regression problem here, right? So it's a nice thing about all of this fitted cube business. So every time I solve a regression problem, I am solving a stationary problem. Right, whether it be LSTD or fitted cube. So every time I am solving a regression problem, I am solving a stationary regression problem. So it's not like the online updates that we were doing where things were non-stationary. So it becomes a little hairy. But now every time I do it, it's actually a fixed data set on which I am fitting.
So we retrain the neural networks every time you generate the data.
Yeah, we do. This is assuming that the cost is cheap.
We're not generating data again.
Huh?
We're using the same data.
No, the experience we are not generating again, but this phi target pair we are generating every time we go around, right? That's what he meant. Oh my God. Exactly. My God, it took you guys so long to get there. Right, I told you what target is, but who gives you the phi? Right? So we spoke about some very simple ways of generating phi, assuming things are going to be linear function approximators, blah blah blah, and things like that, right? But then, how do you come up with phis?
They have to be linearly independent, those things.
Whatever. Nowadays, people don't care about that, right? Nowadays, you know what they do? They throw a deep neural network at it. They don't throw a normal neural network at it. They throw a deep neural network at it, right? And then it learns stuff.
Convergence in that case. If you don't assume it's linearly independent, then
Have you seen any convergence proof for DQN?
I don't know.
No.
I'm not asking.
No. People don't show convergence. They just dazzle you by organizing a public match with the world's champion, Go champion, and things like that. You don't ask them, oh, by the way, can you show me that AlphaGo converges? Right? It just beats the world champion. You don't ask them for convergence, right? So that's basically it. So the proof of the pudding is in the eating in these cases, right? Essentially, it just works. So I didn't mean to imitate him or anything. It just subconscious. Okay. Right? So DQN is a deep Q network that addresses a few of the problems that we spoke about. The first one is it doesn't use a offline set of samples. Okay, it actually samples online. right. So then that's in some sense allows you to not have to worry about the restrictivity of using an offline set of samples, right. The second thing it helps you solve is the phi question. So I am not going to tell you how it solves the phi question, because it requires me to tell you about deep networks. It requires me to tell you about convolutional networks and so on and so forth, right. So let's ignore that for the time being. Okay. Let us say that I give you an input, right. I give you an input. It goes through a black box, okay, that computes a phi, right, and I get the phi at the other side, right, and then it goes through a Q hat network, and I get this, right. So in this case, they basically have. So the DQN is the network that was trained to play the Atari games. Right? Remember I showed you Atari games at the very beginning. So DQN was a network that is trained to play Atari games. So in Atari games you have 17 actions. So you have 8 directions in which you can move your joystick, and then there's a fire button, right, and you can move the joystick in 8 directions with the fire button pressed or without the fire button, right. So that gives you 16, and the 17th action is
You don't do anything. Just
no, right. So don't do anything, right. So that's the 17th action. So there are 17 actions. So you basically you have 17 such networks here, right. 18 is it? What is the 18th action? Just fire and don't do anything. I thought it was 17. Are you sure it's 18? It's 18. Okay. They say it's 18. It's 18. Okay. Yeah, I'm quite sure. Then the 18th action must be don't move the joystick, but just press the fire button. Okay. That there has to be an action for that, right? Right. So yeah. So 18 actions. So there are 18 such networks, and so you get 18 outputs at the end of it, right? This will give you all the Q values. Right. Now you can just go pick your best Q, right? The best action according to the Q function. Perform that, right, and then see what happens to the state. It will go to a next state automatically, and then what you do, you feed that next state into the phi box, right, and then you find the corresponding action, right, and then use that for your Q update, right. Just do it in one shot, right. So you don't actually do this kind of target generation and then have a whole set of things and then do this. You are actually doing online updates, right. So as and when you see a transition, you do these updates, right. But there are problems in doing this, right. So you could potentially run this as a right. You could potentially run this as an online but off policy algorithm, because Q learning is off policy, right. You are learning about optimal policy while you are doing some behavioral policy. And you could also run it as an online algorithm, because you are going to be updating along the trajectory that you are seeing, right. So I am not writing down any equations. All of you know what the Q learning equation is, right. So essentially you do the Q learning, right. That's possible. Okay, there are some problems in doing this online updates for this. So what do you think are the problems? Huh?
Repeat the last one. Problems in?
Problems in doing an online Q learning. Variance. Yes. Can you elaborate on that? Bunch of things that can go wrong. So the first thing is, well, if you go by what the paper, the DQN paper tells you, the first disadvantage they point out is that you are not using the samples efficiently. Right? I'm drawing one sample, right, and then I'm just using it for one update and then I throw it away. Right? Correct? Is there some way of fixing that? Batch mode. Essentially what you do is you basically have a memory, right, and you add your to the memory, right. So, as and when I get an interaction here in the world, I keep adding it to the memory, right, and then I keep pulling these things out of memory once in a while and then I replay them, right. So, I do not necessarily need to have actually seen the state again, but then I will just pull it out of my memory and I will replay them. So, therefore, this memory is sometimes called replay memory. Okay. So, replay memories are not something which the DQN guys introduced, it actually goes all the way back to 93. There is this guy called Longji Lin, right, who did a bunch of actually interesting stuff with RL. So, one of the things that Lin did was this experience replay. So, what Lin's experience replay was is that you remembered entire trajectories like this, right, and you just pull these trajectories out of your memory periodically and then reapply those trajectories, right. So, from the start to the beginning, right, it is just like you are running over the same thing again and again in your head, you know, it is like reliving your life's experience, you know. So, you just did something yesterday and then you just think over it in your head and then you say, oh okay, that is what I did, so let me memorize it or something like that, right. You kind of replay your experience, okay. So, I am not being facetious here, right, it is actually seriously that is one of the things. If you think about it, humans actually do a lot of replay in your head. I mean, you think about what you did, right. So, this is why people play a shot again after they have played it and things like this. So, you kind of replay what you are thinking, right. So, they kind of took inspiration from that and then came up with this kind of replay memory, right. So, but in the Lin version of replay memory, you replay entire trajectories. Huh? That is a difference. So, the way at least, so Rich Sutton talks about planning is that you use these experiences that you have, right, and convert, so go from SA, Si prime R tuples like this, you estimate your probability of S prime given S comma A, you estimate your expected reward given S A prime, right, given S A S prime.
From a state we done simulation and then back up the value of that state.
Exactly. So, this you are not, this is like exactly like having the same experience all over again, right. If you run a simulation, that is different. If you run a simulation, that means you are sampling, you are building the model and then generating a sample from the model, right. So, in the Lin case, you take an existing sample already which you sample from the real world, right. You do not rebuild the model, right. You take the sampled world and then you just rerun the same sample again and again, right. It is like over sampling the same thing again and again, right. So, instead of trying to do a conscious estimation of the model parameters, right, it could very well be the system is very complex, right, and you do not really know what are the possible outcomes, right. So, you just in some way, if you think about it, if you go through the samples often enough, right, you can argue that what you are converging to will be something similar to the certainty equivalence estimate for this data that you have gathered, right. But then you need to have some little bit more constraints on to ensure that, right. So, but replay memory is a lot lighter than actually trying to estimate the full model. You do not try to do a model. For example, in the Atari case, right, your states are continuous, right. So, you are really not fitting a model, right. So, you are really not trying to fit a model, you are just replaying the episodes that you have played. It is just like you play one game and then you just play it again and again and again 100 times. Yeah. Lin's work no, does not sample uniformly, he samples according to the trajectories that are according to the current policy. Huh? Oh, from the memory he samples trajectories uniformly, he does not sample transitions uniformly, yeah, he samples trajectories uniformly, yeah. At least that is what I remember the 93 version of the paper did. He had a follow up version in 96, I do not know if he made any changes to that, but 93 version of replay memory, that is what it did, it just sample uniformly from whatever is there. You just keep throwing them into memory and then sample trajectories uniformly from memory. Huh? Good point, these are all questions to ask, right, these are all different variants that you can explore. So, the original DQN thing, what they did was they just basically had a memory of the last 100 transitions or so, right, the original DQN paper, but then since then there have been many variants that people have played around with, where they throw away some of the trajectories. So preferentially, right, earlier it was just based on history, right. So if you have more than 100 time steps old, they throw it away, right. So now you can start playing around with preferentially retaining more rare transitions in memory and things like that.
The same problem as planning will occur. You can have large peripherals,
Yeah.
not store such large. But
Yeah.
cut the simulation, I mean cut the array at some point.
You have to cut it at some point. Yeah, all kinds of questions will happen. Yeah. So there are lots of issues that you'll have to tackle here, right? Okay. So the replay memory allows us to do efficient reuse, right? So the efficient reuse of samples is taken care of. So what is the next problem that we need to take care of? This comes from the fact that we are doing something that is online, right? So it gives rise to two artifacts. One, if you think about it, my states are changing slowly typically, right. When I am looking at these games, my states are changing slowly, right, and typically my reward also would change slowly, right. So if you look at successive inputs that I am going to see, they will all look very similar, because my states would have changed very little, maybe one enemy moved here and I moved here and the bullet has moved up 2 pixels, right. So the states will look all very similar, right. Therefore the changes, the updates that I am going to be making will be very strongly correlated, right, from one update to the next, right, will all be very strongly correlated. So that can lead to all kinds of problems in the convergence, right. So what they wanted to do was a way of breaking this correlation. In fact, they had problems with convergence when they were actually doing the updates only along the trajectories, right. They had problems with convergence, because every update was very similar to each other. So it's like you're taking the same update and then applying it multiple times, right. So it's kind of messes up with the gradient following that you need to do, right. So what they did was they said, okay, we'll put everything into replay memory, okay. So every time we get a transition, we'll put it into replay memory, but I might not necessarily update for that transition, right. I'll put it into replay memory and pick one transition at random from the replay memory and I will update it, right. Since I am picking things at random from replay memory, I do not have this correlation. So now I might be updating for some state here, right. Next time I might be updating for some other state there, because it might be picked from a different trajectory and so on and so forth, right. So I do this kind of random sampling from replay memory, which is, this is where it is different from Lin's replay. Lin's replay was on trajectories, here the replay is on samples, right. And why are we able to do this? Because of Q learning, and because it is off policy, it is Q learning, and I am using the max over the next state, right. Because of this I am able to do this, right, because I do not remember, I reiterated many times when we did Q learning that you do not have to update along trajectories for Q learning, and here is a case where you actually put it into practical use, right, because you are going to get this from replay memory, so you do not have to. So there is a second artifact that is introduced by doing the online updates. So what is that? It's kind of a biased sampling of the input space, right, because it's going to depend on the actions you take. Suppose I decide to go left at some point, right. So the kind of features I will see will all have the player to the left of the screen, right. So that again increases the correlation between the successive inputs I am going to see. It also skews the kind of samples I am going to get. I am not going to look at parts of the state space which are to the, where the agent is to the right of the screen, right. I will only look at parts of the state space where the agent is to the left of the screen. Right. If you remember, what is this input going to be for Atari? The pixels on the screen, right, just looking at whatever is coming on the screen. So I am going to see only some parts of the state space in a single trajectory, right. So essentially what will happen is only some portion of the state space gets their value functions updated, the other portions of the state space do not. So this can lead to some kind of unbalanced updates in the weight space, right. So and this kind of a transition replay takes care of that also, right. So these are the three main difficulties which the paper lists out. One is inefficient use, and the other one is this correlated updates and the skewed sampling. Right, all of these 3 can be addressed by using a replay memory and picking things from the picking things at the transition level. Yeah.
Can you repeat the last artifact?
Last what?
Last thing that we
Last problem, right?
Last problem.
So see, suppose I decide to move to the left at some point, right? So essentially, then for the next few time steps, right, I will be only seeing the agent to the left of the screen, right? All the states with the agent to the right of the screen will all get ignored. So the sampling I am going to make is strongly driven by the policy that I have taken.
So we capture the whole screen, isn't it?
Yeah, but the whole screen is there, but that is just one state, right? The screen with the agent here is one state. The screen with the agent here is a different state, but what I will be seeing is only some subset of the states, right? So that subset is determined by the policies I am taking, the actions I am taking, therefore things can get really skewed up, right? So only one side of the screen or only one part of the state space will get updates, the other parts of the state space does not get updates. So this can lead to some kind of a because this side is all incorrect values, right, and this side is all getting correct values, but then they might get updated by the incorrect values here. So things can get completely messed up. So you really want the whole state space to get some kind of uniform updates, so that you don't mess up the overall backup process.
So this problem was there in other online these things also, like in SARS also we had.
The other online methods also had this problem. That's a good point. It really didn't creep up in the empirical setting until we moved on to such large state spaces, right? So only when you went on to such very large state spaces where you had a significant difference, it became a problem.
So it's not the problem with neural networks. The problem
It's
with
not the
large.
problem with neural networks at all. It's just the problem of doing online updates. I didn't say it was a problem with neural networks. It's a problem with neural networks to the extent that the function approximators now become so complex, right? So what you do in one part of the state space can very non-deterministically affect what is happening in another part of the state space. Earlier when you are looking at linear function approximators, things were a little bit more comprehensible, right? So now people just take stabs in the dark saying, oh, this might be what is wrong, and then they try fixing it, and if it works, then they conclude that was what is wrong. Okay, so that's essentially how you do work with this really multi-layer complex neural architectures. You really don't know what is going wrong. So you make hypothesis, you try fixing this, you really do science now, right? So you make a hypothesis, you try fixing it, and if it works, great. If it doesn't, you go back and change your hypothesis and try something else, right? So that's essentially what you do. Right. So good. So any other questions on this?
Do they take advantage of symmetricity?
Sorry, take advantage?
Symmetricity in the game.
Yeah, maybe.
If your phi function does, then great, right? You know all about convolutional neural networks. Do they take advantage of symmetry? Depends on the kind of symmetry. They don't take advantage of all the symmetries that are there, right? So depends on what the phi network does. So if you can actually start injecting ways of taking care of symmetry there, then great, right? So, sorry.
You will be doing deep learning basics in RL?
Sorry?
You will be doing deep learning basics in RL?
No.
This.
No, that's all. That black box there, that phi is deep learning. Okay. Any other?
So is deep learning used even in the function approximator over there?
Even in the function approximator where?
Is it just a normal 2 or 3 layer neural networks, or
The
is
Q
this
prime?
Yeah, Q primes.
So remember Q prime is a 1-layer neural network, right? Let's take the DQN and then you have a completely connected layer, that is your Q prime, right? Multi-layer, is it? Only one layer, yeah, it's a 1-layer neural network. So this is, the original DQN is 2-layer and the current version of DQN is 3 layers, but it's a convolutional neural network, so it's not layers as you normally understand it. And this is a 1-layer network that takes the output of this and chucks out. Well, it's not one network, it's 18 different 1-layer networks. I mean, you're not restricted to use a neural network there, right? Your Q prime could come from anything, right? As long as you can compute a gradient through it.
So the deep is referring to the phi over there.
Well, considering that Q prime is actually a neural network, so if you think of it, it's like a 4-layer neural network, right? I split it up as phi and q prime, but if you think of it, it's actually a single box from the input to q prime. So it's like a 4-layer neural network. The first 3 layers are of one type, and the 4th layer is of a different type. Right. So I mean, you're just talking semantics. I mean, you can apply that deep to anything, your thing. So if you want to say, oh, we are only doing deep representation learning, on top of that I am doing a 1-layer neural network for regression, yes, sure, you are welcome to say that. Right? There is no, I mean, there is no standard nomenclature here.